Let's look at an example here dealing with velocity, which is going to be our instantaneous rate of change. Specifically, we're going to be given a function here with how distance and time are working together. So it's going to be, if you have a function that's dealing with distance and time, the rate of change will be velocity, because that will be like miles per hour and things like that. So what I'm going to do is show you here how we can kind of go about this a long way, and then I'll show you using Desmos how you can use it to kind of speed these types of problems along. So we have a rock is shot upward with a velocity of 80 meters per second. The height after t seconds is given by h of t equals 80 plus 48t minus 0.5t squared. So we're going to find the average velocity over these different time intervals. So like we're looking from 30 to 31, 30 to 30.5, 30 to 30.1, 30 to 30.01. And with that, this is going to get at the idea of instantaneous velocity, because we're looking at this average rate of change as we're getting shorter and shorter intervals. So like in terms of the graph, if we have our coordinate at 30, we're looking at the average rate of change, or that secant line, but then we're getting closer and closer to that x equals 30, and that's going to approach creating the tangent line. So with that, we can predict the instantaneous velocity after 30 seconds. So let's look at the average rate of change for these scenarios. So what we're going to want to do is, if we're looking from 30 to 31, I'm going to have the coordinate 30 and then some y value, and then I'm going to have the coordinate 31 and some y value, all coming from 80 plus 48t minus 0.5t squared. So let's grab my scientific calculator. What I'm going to do is try to see all of this at once. All right, we're going 80 plus 48 times 30 minus 0.5 times 30 squared. And that's 1070. Now I want to do the same thing for 31, and what's nice about the Desmos Scientific Calculator is I can just edit this. So wherever I put 30, I'm just going to change that to 31, which is 1087.5. So the average rate of change is going to come from the difference in the y values. So 1087.5 minus 1070 all over 31 minus 30. And we'll plug that into the calculator. So let's see, I'm going to have a fraction all over 31 minus 30 is 1. So 17.5 would be my average rate of change from 30 to 31. So now I want to do the same thing, still at 30, 1070 for one coordinate, but now I'm going to change the x coordinate. 31, it's just a bit too far away, so we want to scoot closer to 30. So I'm going to do the same thing, but using an input of 30.5. So to get that y coordinate, I'm going to go back to where I had plugged in 31 and change that to 30.5. So 1078.875. I'll try to keep that as accurate as possible, because the more decimal places we plug in, the better. So we're going to change that in the numerator, minus 1070 over 30.5 minus 30. So with that, we're going to now calculate 1078.875 minus 1070 all over 30.5 minus 30. So now it's 17.75. So we actually had a little increase there in our slope. But now let's say that was also too far away, so we want to scoot a little bit closer. So we still have 30, 1070, but now our next x-coordinate is going to be 30.1. So let's see what our output is when we have 30.1. So 1071.795. So finding the average rate of change between those 2 points, we'll have 1071.795 minus 1070 all over 30.1 minus 30. So with that, let's see, 1071.795 over 30.1, 17.95. So it increased a little bit more there. So you can see our average rate of change, it's getting a little bit steeper each time. So as we're closing in closer and closer to 30. So now let's do one more using the 30, 1070, but now we're super close to 30 at 30.01. And I mean, we could keep doing this. We could get closer and closer to 30. Like we could go extreme with like 30 and 30.00001, something like that. And that would really be getting close to our instantaneous rate of change. Because basically we want the difference to be the idea of zero. We want it to approach zero. So that's what we're trying to get at here, is getting closer and closer to that point and evaluating the slope of our function around that point. Okay, so if we're dealing with 30.01, the output for our function is going to be 1070.17995. So average rate of change, might be getting used to this with the calculator. We're just kind of moving these pieces around. So let's see, 1070.17995. So we're super close to that 1070, and we're doing 30.01. So now my average rate of change is 17.995. So what I'm seeing here is as these points are getting closer and closer together, this average rate of change is getting so close to 18. And it's that idea of getting super close. I think if we took that instantaneous velocity, we would have an instantaneous velocity of 18, because that's what our average rate of change is approaching as those x values get closer and closer together. So it's that type of dynamic that is the idea of instantaneous rate of change. That idea of what's happening in an instant is you're trying to get x super close together, almost so that it's the same, but we need 2 points in order to evaluate the difference. So with that, we can get an idea of the trend by kind of going further away, but then getting closer and closer. So instantaneous velocity, we're looking at t equals 30. So after 30 seconds, the rock is increasing, or let's say the rock has a velocity of, because that's really what we're getting at here, has a velocity of 18 meters per second. So at that moment in time, we can get an idea. Again, we have these average, like from 30 to 31 seconds, on average it was changing by 17.5 meters per second. Here, it's just right at that 30 seconds moment, the speed or the velocity of that rock traveling was 18 meters per second.